Welcome, everyone. This is day 3 of the Microsoft Connect conference. I am Richard Garris. Today, we're going to talk about how you can build your first application using Apache Spark on the new Azure Databricks platform. A little about myself. My name is Richard Garris again. I have 14 plus years doing advanced analytics and big data solutions for everyone from Fortune 500 companies to small startups. I have degrees from Carnegie Mellon as well as Ohio State. Go Bucks. During the course of the session, if you have any questions, please don't forget to write those in, and I'll try to answer those as we go through our presentations today. So a little bit about our agenda. First thing I'm going to talk about is Azure Databricks, the newest offering on the Microsoft Azure platform. I'm also going to talk about data platforms, a little bit of history, past, present, and future. I'll also talk about ETL 2.0, the new ways to do ETL in the cloud. Talk a little bit about Apache Spark data frames and data sets, as well as talk about Databricks Delta and streaming. So first, Azure Databricks. So Azure Databricks is a product developed in conjunction with Microsoft as well as Databricks, the company behind Apache Spark. So it's designed as a one-stop shop for doing all of your analytics. It's the one unified platform for doing both advanced analytics as well as doing SQL. One-click setup, easy streamlined workflows, supporting your favorite programming languages, including Java, Scala, SQL, Python, and R, as well as enterprise-grade security. So integration with Active Directory, integration with encryption, as well as all of your favorite compliances, including ISO 2007-1 and SOC 2. So a quick view of the platform itself. So on the left side, you see all the different data sources you have within the Azure platform, everything from IoT and streaming, cloud storage, your SQL data warehouse, maybe you have Hadoop. And on the right side is all your applications. So you have machine learning, you have BI applications, exporting your data to third-party sources, as well as your data warehouses. Often enough, there's a lot of complexity in between getting from the left side of the screen to the right because it involves a number of different personas, data engineers, data scientists, business analysts, multi-stage pipelines. These are very complex things to build. Within Databricks, we have the one unified platform, allowing you to build these applications in a way leveraging Apache Spark, and using technology we call serverless, which allows you to use the virtual machines within Azure in a way that's both cost-effective as well as performant. So a little bit of history. So in the first generation of databases, we had the data warehouse. Largely, it was very built on the concept from Boyce Codd relational databases. It was limited to just SQL. The processes were very rigid. It was very hard to put data into it and get data out. And it was very limited. As an example, even adding a single column to a star schema in a data warehouse could take months of effort. It involves changing your ETL layer and then changing your load processes and then finally adding it to your column. It could be a lot of effort. So what came along next was the Hadoop data lake. So the whole idea was instead of having schema on write, let's have schema on read. This gives you a much more agile way to actually store and analyze data. So the whole idea was you can put a whole bunch of data into your data lake and then be able to do analytics on the outside of that. The reality is, though, it's very hard to get that data out of Hadoop. There's many different solutions that are out there, including using MapReduce, using different tools like Storm or Mahout. But generally, you had specialized engines. It was very hard to actually build one unified platform. So here at Databricks and at Microsoft, we put together the Azure Databricks platform to be the unified analytical platform for doing all types of analytics. Everything from machine learning to streaming to SQL, real-time query analysis, all within a single platform. We also enable enterprise collaboration using our collaborative workspace. So it gives you one place, one single pane of glass for doing your analytics. So slightly differently, using the analogy of the mobile revolution, the first version of the mobile phone looks like this. I actually had one of these. It was just a dumb phone. You dial a number, and it calls. You can call from anywhere. So it was very powerful at the time, but very limited. Then along came these specialized devices. So I had a Palm Pilot, a BlackBerry, I had a Game Boy, and they're all different devices. They all do one thing, but don't do everything well together. This is very similar to the world we see today in analytics. Then along came the iPhone or the Android phone. And these are like the one unified platform. So you can do really interesting things like take a picture, take a video, share it on your social media, as well as organize your day and your calendar, all within a single device. Likewise, I'm just going to build out the slide. We see Spark following a similar journey to the journey of mobile. So you had Hadoop, which is the one specialized engine that finally gave a single platform for doing distributed computation. Along came a whole bunch of specialized engines, in this case Hive, Storm, Pig, Mahout, for doing all different types of workloads. But they didn't work well together, and you had to learn specialized skills for each one. And then lastly, we have Spark, which is the one unified engine that allows you to do all these activities, but in a single framework. So this is a view of Spark today. This is an open source, part of the Apache Foundation. So it includes 4 different programming interfaces: Scala, Java, Python, and R, as well as 3 different kinds of data, ways to analyze data. One being data frames and data sets, which we'll talk about more, live data or streaming data, as well as ML pipelines. So the 4 key components of the core, underneath the core Spark engine are Spark SQL, Spark Streaming, MLlib, and GraphX. And then from there, you can actually analyze all kinds of data, whether you're looking at data in Hadoop, like HG Insights, Azure Blob Storage, looking at sources such as like Postgres or other SQL databases, as well as NoSQL storage layers like Elasticsearch or Cassandra. So now a little about ETL 2.0. So ETL is not new, been around for a long time. We've always had companies like Informatica as well as Ab Initio, who are the pioneers in doing ETL. But ETL is changing with the advent of big data. So a little bit about Hadoop, for those that haven't done a lot with big data. Hadoop was largely based on 2 concepts. One was called HDFS, or Hadoop Distributed File System, which is your data layer, and then MapReduce, which was the actual engine for processing data. Those are really the 2 main components that launched the Hadoop revolution. Spark is a next-generation processing engine based on in-memory processing and based largely on Java and Scala. So the difference between this and Hadoop, there is no storage in Spark. Spark is just purely a processing engine, and we made the code much simpler. I'll give an example of MapReduce code on the next slide, but very simply, we have a file, we call a map function on that, we do reduce by key, call a filter operation. So 3 lines of code, and then you're able to do this kind of execution, which you see on the bottom, mapping that function across multiple nodes, calling a reduce function to shrink your data set to the exact combinations or aggregations you want, and then finally filtering it out and then displaying it back to the user. From a code perspective, MapReduce is very verbose. So you see a lot of different lines of code here. In fact, it's scrolling down to the bottom of the screen, so you can't even see the last few lines of code here. That same operation, this is simple word count, is only 4 lines of code in Spark. So it's a much more concise and very readable way to do big data processing. So a little bit about the history of Spark. So Spark started in 2009, so it's almost 8 years old at this point. That's about 600,000 lines of code. Majority of it is Scala. Our last stable release was in July 2017, Spark 2.2. Spark 2.3, as well as the next generation of Spark for next year, are well on their way through the Apache Release Foundation. So in next month, we should see that coming out very soon. It's built by 1,000 developers at over 200 different companies. So it's a very popular project. In fact, it's the most popular project in all of big data. So if the reasons behind the last couple of slides don't convince you that Spark is the way to do big data in the future, here's a couple other stats for you. Number 1, it is the second most trending technology on Stack Overflow, just behind React. Well, actually React is well ahead, but if you're looking at doing kind of data processing, Spark is well ahead of any other technologies out there. And if this doesn't convince you, the pay is good. So if you look at Spark versus any other technologies today, you see that Spark is in the leaderboard with 125,000. That's a median level of income, with F# and Hadoop being in the 115 range, and then others are slightly below that. So every year we do a survey at Databricks through the community to find out what are the top applications for Spark. This includes both Azure Databricks as well as open source Spark. So BI is the dominant use case that's used within Spark. Second is data warehousing. And then third is recommendation engines. And you can see the others: log processing and user-facing services. So it's very basic. Spark is distributed computation. It involves really 3 different components. First is the driver, which is the actual orchestrator. It's almost like the orchestrator for a band. The driver is what drives and manages the entire process from end to end. On the other side, on the far right, you see the workers. The workers are the actual machines actually executing whatever job they're being given. They're called the workers themselves. Within the worker has an executor, which executes individual tasks that are required. In the middle here, the cluster manager is the coordinator between the driver as well as all the workers. Okay, so I'm going to start with data frames and data sets. This is the primary way people actually do data analysis within Databricks and build applications. So this is really the way you would start doing your ETL processes using Apache Spark. So the first thing to note is that unlike a relational database, you can analyze all kinds of data and all kinds of sources. So you can have unstructured data like text, logs, tweets, articles, sound data, sensor data, genomic data. You can also analyze structured data, so key value storage like Redis Labs or Cassandra. You can do tabular analysis, so you can connect your data warehouse, you can connect your Azure or SQL database to Databricks to do analysis out of that source. You can also analyze graph, geocoded, as well as time series data. So the older interface within Spark is the RDD interface. So you can think of it a little bit like analogy of assembly versus doing things in C, C++. So assembly is good for doing very low-level analysis, but generally most programmers today won't go to like hand-rolled assembly to build applications. It's just too time-consuming and too much effort. But that said, you can write very fast applications using pure RDDs, just like you could with assembly. It just takes more work. So an RDD is a resilient distributed data set. It's really a partitioned collection of objects spread across your cluster. And it's either stored in memory, in the actual RAM of the machines, or it references to places on disk. So the RDDs are built around very simple transformations, maps, filters, joins, as well as actions, count, collect, and save. One thing to note about both RDDs as well as data frames, they're actually built for resiliency. So if a machine was to crash, like a VM within Azure Databricks was to crash, Spark will automatically recalculate that value from another machine automatically. You don't have to worry about the whole job failing at that point. So really quickly, visually, this is how an RDD works. Each of your different items in your distributed collection is selected, and using a hash, it's mapped to an individual worker. So in this case, you see there is 5 partitions with different items in each of those partitions, and they're all mapped to, in this case, 3 different executors. So as you do your analysis and do your work in Spark, one of the ways to increase performance is to increase parallelism. So for every partition, you're going to have another task to do work. And so the more tasks you have, the more partitions you have, the faster the job goes. Only to a point, obviously. If you have too many partitions, then you can run into too much parallelism, which will actually slow down your job. So Spark RDDs are really built around the idea of a closure. So a closure is a closed-ended function that is run against a set of data. You can think of it like the map operation in Scala or Python. And so if you're writing code in your Java or Scala front end, it's actually executing that code in the JVM. If you write it in Python, it's actually using the Python backend. Python closure is typically slower in Spark than Java because it has to go outside of the JVM to actually do the execution. Data frames are a bit different. Data frames are built on the exact same execution engine, and you're only providing high-level code. So whether you write your code in Python, Java, Scala, R, or SQL, you're still using the same engine to actually execute the logical plan. So within the logical plan, you're actually building, in this case, Java bytecode to do the actual physical execution. So it's much faster using data frames out of the box and using RDDs. So this is kind of a summary of what we just discussed on the previous slides. So again, RDDs are a collection of native JVM objects. There's built-in compile time safety. It's easy to express your logic, easier than map reduce. You can have lots of existing code plus users, and low-level control of Spark. So you can make an RDD maybe as fast as a data frame, but it's much harder to do, many more lines of code. Data frames and data sets, or SQL, all use the same binary engine, which we call Tungsten. It gives you better performance in terms of lowering garbage collection, as well as better use of memory, faster sorting, hashing, and serialization, which again increases your overall performance. And more, you're giving more of the job of optimizing the code to the engine as opposed to doing it yourself. So we can do a lot of optimizations under the hood by using data frames and data sets than doing it yourself with RDDs. This is represented on this slide. So you can see here in the light blue, this is the data frame code. So the data frame code is all at the same speed regardless of your interface, SQL, R, Python, or Scala. But if you look at Python and Scala from an RDD perspective, Python is significantly slower than the Scala version. And then again, the RDD for Scala is also significantly slower than using data frames. So in summary, both RDDs as well as data frames both allow compile time safety. And we try to, as much as possible within the APIs, allow you to do compile time checks. So what this gives you is that before you actually run your job, we'll do checks within Databricks, within Apache Spark, to make sure your code compiles, it executes, there's no errors in it. One of the risks when you're dealing with very large data, if you're going to run a job that takes 2 hours, you really want to know before you kick off the job that something's going to fail. So one of the key things you want to do within your design and as you build out your applications is to take advantage of this compile time safety. Okay. Databricks, in terms of our platform, the most popular language at Databricks in terms of our users is actually SQL. So everyone obviously knows SQL from, this has been out since 1980. It's the most popular language for doing data analysis. So Databricks, as well as Apache Spark and Azure Databricks, can run actually 104 TPC-DS queries as of Spark 2.x. It's SQL 2003 compliant. One of the things we did earlier this year, we released a blog post that showed that the Databricks is significantly faster for running the TPC-DS benchmarks compared to any other engine running Spark. So this is what it looks like under the hood. So whether you're writing SQL, data frames, or data sets, you write your code, then the Tungsten engine will the Catalyst optimizer will create a logical plan for how to execute that job. Then you'll see the actual physical plan, and I'll show you an example of what that looks like. And then we actually generate real code. So that real code is actually executed, and then it'll actually pull data out of the data source that's chosen. Let's use Azure Blob Storage as an example. And then it'll actually execute whatever plan is provided. So going a little level deeper than this, you can see here that once you get that logical plan and figure out a cost model, so within databases, there's a concept of a cost-based optimization, which is looking at the cost of different kinds of joins, looking at how do I organize my predicates, organize my filters, so it's optimally execute whatever code there is. We built that into Databricks as well as into Apache Spark. We call it the Catalyst optimizer, and that allows you to just simply write your business logic and not worry about tuning your code. Okay. So this is an example of a physical explain plan. I won't go through this in too much detail. Essentially what it's saying here is these are the steps that are going to be taken based on your query. This may look familiar to you if you used SQL Server. So the whole idea is that if you were to do a simple count query, do a filter, join with another table, this would be like the example plan on the first line. You do the aggregate of a count, you'd do the filter first, and then you would execute your subquery. That's just an example. So simply put, in a four-step process, you're doing the analysis of the actual execution to resolve any references. You do your logical optimization, so you figure out the most optimal way to execute the plan. Then you do your physical planning. You figure out actually how to query each of those different sources. And lastly, you generate actual code. So again, Spark is written in Scala based on the JVM, so we generate Java bytecode. All right. Let's skip ahead a little bit just so you guys can see some more details here. So if you look at logical plans and physical plans, these are a couple different examples of that. The logical plan would be joining and filtering. A physical plan is actually scanning individual files, as well as scanning and doing a join and where that join is going to happen, as well as how it's put together at the very end in terms of both optimizing both the physical plan as well as logical plan. So a couple examples of optimizations built into the platform. One is called predicate pushdown. What this means is that one of the most expensive operations in Spark is processing a lot of data. So one of the things you want to do is you actually want to prune down and reduce the amount of work required to do this type of query. So in this case, we're doing a simple read of a JDBC source. In this case, it's Postgres. It could be any JDBC source for whatever reason. In this case, we're looking for a people table, and we're looking for a person named Michael. So one of the things that we do within the Spark engine is that says, okay, well, I'm only looking for people named Michael, so it doesn't make sense to read in the entire people table loaded into memory in Spark and then find Michael that way. So the more efficient way to do this is to push down to the actual engine, in this case JDBC, the where clause. So we push down the where clause of Michael into, in this case, Postgres, to only pull the data required for this type of analysis. So this also works in distributed file storage layers like Blob Store if you're using a format like Parquet. Parquet itself supports predicate pushdown by limiting the number of files read by the Spark engine, so it also improves your overall performance. Another optimization is what we call efficient joins. So for those of you, that have worked in data warehousing or worked with SQL Server, this looks very familiar to you. There's many different kinds of joins. One example is a sort merge join. Another is a broadcast join. So you use a broadcast join in cases where you have a very small table and a very big table. So the most efficient way to join those two operations is take the very big table and then have that distributed across multiple nodes. Have the very small table broadcast all the data to each of those nodes and then combine the two together. But if you have two very big tables, let's say DF1 and DF2 in this case, and they're both very big, it doesn't make sense to broadcast a big table across multiple nodes. It'd be very expensive from a network's perspective. And so in that case, we do what we call a sort merge join. So we take both of the keys, we do a sort on those operations, and then we would actually put those matching keys in the same physical node to do the actual join and then output the results. So part of what Catalyst is doing is figuring out, based on the size of different data sets, what type of join to do given the situation. So a little bit more about data sets and data frames. So I mentioned these terms, but I didn't really define them. So you can think of a data frame as an unstructured data set, for lack of a better term, or a data set of type row. You can think of it almost like a class of the very specific data types. In Spark 2.0, we merged the APIs of data frames and data sets into one thing, just to make it much simpler from a code maintainability perspective. So as an example of how you would actually use a data set, you take a data frame, which is usually a set of columns, do as on that, in this case this is in Scala, and provide a class name. So a very simple way to actually represent data in a distributed sense. So in summary, over the long term, RDDs will remain the low-level API in Spark, much like you would with assembly. It's not going away. But data sets and data frames give much richer semantics and optimizations above and beyond what's available in RDDs. And all of our major libraries, including the new structured streaming library, MLlib, and graph frames, are all taking advantage of optimizations in data frames. So again, in summary, RDDs provide functional programming. They're type safe, but data frames support relational operations like multiple joins, Catalyst query optimizations, tungsten operations in terms of how we manage the memory and the RAM, just-in-time code generation, and then sorting and shuffling without having to do serialization and deserialization, which is a very expensive operation in distributed computation. Okay, so a little bit more about Databricks. So again, Databricks is a commercial version of Apache Spark. So Apache Spark, out of the box, is really an engine, and Databricks is more like the car, like the Tesla, for running Spark in the cloud. So it gives a couple different things that above and beyond Spark. One is called Databricks I/O, so that's more efficient predicate pushdown, as well as the ability to actually optimize certain data sources, including Azure Blob Storage, as well as Databricks Serverless. So it gives you a platform that easily lets you scale up and scale down the number of nodes very quickly, so you don't have to worry about managing those resources and managing your costs. So one note about Spark, and this is true of all distributed compute technologies, it's really built around the concept of linear scalability. So one of the concepts there is that if you have, let's say, a job, a terabyte of data, and it takes like, say, 2 hours to run your job with 1 terabyte of data, you could double the number of nodes, let's say going from 10 nodes to 20 nodes, and in theory, cut your runtime in half. So that's the idea of linear scalability. So a little bit more about Databricks Serverless. So again, Databricks is a fully managed cloud service in Azure. You can easily set up your compute resources, and you can set up and run both SQL, Python workloads. In terms of elasticity, you can also automatically set up your environment to scale both your compute as well as your SSD and local storage on your VMs based on the actual workload. This helps you manage your costs, and it allows you to just push a button and not think about how many nodes you need for a particular job, as well as fine-grained resource sharing. So unlike other versions of Spark, which require you to actually specify the number of nodes, amount of memory, and RAM, all you would do is connect to a cluster and then run your job, and we will take care of the rest, and also be able to manage both the cost as well as the performance. So a little bit more about our security. So within Databricks, we have end-to-end encryption. We worked in conjunction with Microsoft to make sure that it meets all the security standards of the Azure platform. From terms of operational security, we're the one platform that has security and access controls around notebooks. So within our collaborative environment, which I'll give you a short demo of that, you can control access to that notebook, including read permission, write access, manage permissions, as well as those permissions on clusters, jobs, and tables. We also integrate with the single sign-on solution available in Azure, the Azure Active Directory. It allows you to set up whatever single sign-on you'd like within your enterprise. We provide audit logging, secure integration with BI tools, including both Tableau as well as Power BI, as well as compliances with SOC 2 Type 1 and 2, as well as HIPAA if that's required. So Databricks workflows is very important for data engineers. One of the key things within our platform is we give you different options in terms of being able to schedule and run either notebooks or jar-based jobs using our notebook and our job scheduler. It's point and click, literally one click. You can have a job that runs every night or every day, or for the streaming job, you can click it off to run, and we'll automatically take care of fault tolerance and rerunning the job in case of failures. Okay, so again, just to reemphasize our collaborative workspace. So our collaborative workspace is a notebook-based environment for running various Apache Spark jobs. We have different options for both data engineers, data scientists, as well as business analysts. A couple different ways that our data engineers use our tools is to actually write their code in a notebook. This is very powerful because it gives you a lot more flexibility and ways to experiment on your ETL type jobs. Your data science teams can use our interactive notebooks to do machine learning, advanced analytics, AI within the same platform. And they can use the language of their choice, whether it's SQL, R, Scala, or Python, and then use built-in visualizations to do some simple analysis, or use their favorite third-party visualization library, things like ggplot as well as D3. So for analysts, they can also take this, or excuse me, data scientists as well as data engineers can actually publish dashboards. And then all that the business expert has to do is go into the platform, look at the dashboard on a daily basis, and look at their analysis and make a decision of some kind. Okay. So for additional questions or looking into Databricks and the Azure Databricks platform, you can either go to azure.com/Databricks, or the inverse of that, databricks.com/Azure. So we coordinated this, and we have a little bit of recursion going on. So it gives you like the one place where you can go in to get some more information about the Databricks and Microsoft integration. So with that, I'm going to go into an example. Okay. So I'm in Azure Databricks. So again, this is the latest offering available on the Microsoft Azure platform. So when you sign up for Azure Databricks through the dashboard, we're currently in private preview. This is what you'll see. You'll see a single pane of glass around how you can do a data analysis. We have a number of different notebooks to introduce you to various parts of either Apache Spark or overall data science, as well as structured streaming if you're trying to do some type of real-time processing. So the left sidebar here, you see the different sections of the application. And the home button, you actually see your workspace. So it's very much similar to your desktop. You see both your notebooks as well as your libraries you might load onto the platform. And here we see our data. And these are all various tables that are stored within the Azure Databricks platform. In Databricks, everything is by reference. So these aren't actual tables like you would think of in SQL Server. Instead, they're actually files, in this case, sitting on Azure Blob Storage. So I'll go into more detail about the clusters page in a minute, but these are all the clusters that are currently running in the platform. And this is our job scheduler. So these are the list of jobs that are being scheduled by various people, in this case on my team at Databricks. Okay, so if I go back to the tab here, I'm going to go through one example. Within Azure Databricks, we support notebooks. So notebooks are a popular way for data scientists to do data analysis, but it's also a tool that is increasingly being leveraged by data engineers for doing data munging and data extract, transform, and load. The reason for this is it's very easy to read, easy to consume, and easy to maintain. So in this case, I'm using what we call Markdown, Markdown is a way to document code in the same place that you'd actually run it. So it's very powerful if you're trying to document like why you're changing a certain column value, maybe some tips and tricks around performance. You can document those here. You can also do things like comment, so it's very good for code review. So you can say, this is not the right image. Pretty simple. We also have built-in revision history. So one of the things that gives you is the ability to track and gives you that governance around your ETL processes. So anytime you actually make changes to this notebook, it automatically gets tracked here in the revision history. You can also tag certain versions, saying, let's say this is the gold version, as well as link it to your favorite repository, whether it's GitHub, you may be using Microsoft SourceSafe. It gives you the ability to actually version control these notebooks just like you would any other source code. And again, just to emphasize, I mentioned this before in the presentation, you can actually share this with other users in your system. So let's say I want to share it with Stephen Yu. I give that person, in this case, Stephen Yu, just read access, add them to the environment, save it, and then now you have Stephen Yu that's able to collaborate with you on this particular notebook. Okay, so just a little bit about the data set. So this is a static data set. This is looking at single-family mortgages from Freddie Mac and Fannie Mae. So it's a file I downloaded on the internet, but it gives you the ability to actually to see different features within the platform and how you would ingest data and do different types of ETL. So a couple different things we have in terms of shortcuts. So this is actually written in Python. You can also write your code in Scala, Java, or SQL. But you can also mix and match languages and take advantage of what we call magic tags. So this %fs link is doing a simple list file of these files in this container within the blob store. So here I see Freddie Mac, and I'm querying this folder called loans, and then I can run this code here. In this case, I'm doing Shift-Enter to run that. I can also do a plus here to run that. I see here's a bunch of CSV files in this directory. They're quite large. In this case, they're about 60 gigabytes per piece. I can do a quick head to see what the data looks like. I can see it's just text. And then I can actually load this into what we call a data frame. So you can think of a data frame a bit like a table. But instead of a table being something imported into a relational database, which is a black box, instead it's actually referring to the CSV file and turning into something I can then consume further down. Excuse me. So again, let me show you what's going on under the hood here a bit. So in this case, we're actually running a series of distributed jobs. I'm going to open this tab to show you what actually happened here. So in this case, what it's doing is actually running a series of, one command. It's doing reading in the CSV file, but it's using a number of different tasks to actually execute that. So visually, this is how it's actually executing that. It's executing that on a series of different executors. You can see here that these are different tasks, what they're executing, what the executors are actually doing. Okay. Let me print the schema out of what actually got produced here. So in this case, these are the various columns in this data frame I created. I can also do a quick display of that or show of that. So SFDH. I just copy and paste here. So it's actually going to show you what this actually looks like. Give it a minute. While it's loading, I also want to show you another example of how you could do this. Oh, there it goes. So here I see some text data with the way this looks is how you do this in open source Spark. Within Databricks, we also have an option to do display to make it much cleaner looking. So display, this will use an HTML-based table, so it'll be a little easier to read that. So while it's loading, let me show you a different way to do this. So if you don't want to do things in code, in that case in Python, you want to do it using just pure SQL, you do that as well. So in this case, I listed out all the different columns of the data set using standard SQL. I'm using CSV as my format, give it the path I want to load. Say it's delimited by, in this case, the tab character, and it has a header. And then I can actually create a table that way as well. You can run that. And this is the nice review of that. So this is what the table actually looks like. So here you see whether the loan came from Fannie Mae or Freddie Mac, the record ID, some various codes, the amount of the loan, as well as some other fields that are available in this CSV file. Okay. So under the hood, and I mentioned this about the physical explain plan, you can also run a simple explain. It'll show you actually what's going on here. In this case, it's doing a file scan of the CSV file. It's reading in all these different columns. There's no filtering. There's no other changes. And so you can see here, this is how you can get a view of what actually is executing under the hood. So, as a data engineer or data scientist or any other data person, the first thing you're going to do is explore your data. You're actually kind of trying to find out like what it looks like. Does it have the right fields? Is there any kind of dirty data or anything that I need to clean up in order to load this into my my virtual data warehouse? So this is a quick example of like looking at a single record, making sure that that record looks good, which it does. I can select individual columns. In this case, I'm looking at one column, which is called unpaid balance. Maybe I'm interested in this because I want to see how many people have loans outstanding. I can also do things like look at the some different metrics about this individual data. That's what's done with Describe. So I'm running a bunch of different code here. I was running 4 different tasks, executing that in parallel. So one of the things I did, let me see if it's actually doing that up here. Yeah, so I added a couple of the nodes to this. I set up an auto-scaling cluster. What it gives you the ability to do is actually add additional nodes to the cluster as I do more work on it. So it's a good way to manage your overall cost of executing jobs in Databricks. All right. Awesome. So then I did a quick describe command. So I'm going to show you a couple different things. So one of the things built into the platform is the ability to do quick visualization. So this is the one column unpaid balance. So these are all the different numbers here. But let's say I wanted to get a quick view of like what is the overall, in this case, what we call a histogram, the density of various dollar amounts. So in this case, I see that majority of loans are somewhere between the area of, let's say, 60,000 up to, 200,000 is kind of your average, and then you have a few more that are in the higher dollar amounts. I can also see this using a quick describe command. So I see here the number of records as well as the mean, min, and max of that same field. I can also look at the unpaid balance over time and look and see that in 2010 we had a spike, and then we've slowly been climbing up a little bit in terms of the unpaid balances of people's loans. So one of the key things, so you saw it before, these queries ran a little slow, right? It wasn't that fast. So one of the best practices around how do we do data analysis in the cloud is to use a format which we call Parquet. So Parquet is a columnar-oriented storage format, meaning that we store all the data within a single column in the same file. This is really powerful because most of the time when you're doing analytics, you're not looking at all the columns, all the columns and all the rows and all the data. Instead, you're actually looking at aggregations and summations. So that's why when you use things like Parquet that are columnar, the queries tend to run much faster. So in this case, I'm taking this table, which I call loans, which is in CSV. I'm going to do an overwrite, change the format to Parquet, and save it as a table called loans optimized. So you can see like how much faster this ran. So before I had this graph up here, I ran this, took 15 seconds to run this query above. But now when I run it with Parquet as my format, it takes just a little over a second, so 1.35 seconds. So it's significantly faster, and I can do my line chart the same way I did before. So I can see what it looks like by looking at the actual table format. In this case, rather than being a CSV, is now in optimized Parquet format. Okay, so a couple of different techniques to do data munging within Databricks. So one of those ways is what we call user-defined functions. So in this case, I'm creating a Python function called purpose of loan. So my data dictionary that I got from Freddie Mac, it said that the loan purpose is 4 different values. It has one being the purchasing, 2 being refinancing, 3 is a home loan, and 4 is not applicable. So I create a quick map within Python for this, and then I say if the code is in that value, return that code, otherwise return none or null. So that's the actual function I've done here, and I've registered that in the SQL engine. Now that I've written that code, I can actually call this function called purpose of loan within a SQL context, and I can actually see right away, here's the actual values for that single column. So another way you can do this is what we call data sets. So I'll talk a little bit about data sets in the talk. So I'm going to show you, in this case, some kind of messy data that may be hard to reason about. So one of those, in this case, is the borrower's ethnicity or race. Those are stored in 5 different column values. So I can see here that this is their primary race as well as other races they might have checked on their application form. This is tracked by the US government mainly to check how various lenders are behaving in terms of making sure that they're following good loan practices. But it's not really that readable. I mean, there's a bunch of numbers in different columns. So one of the ways that you can do this is to use what we call data sets to actually do the munging. So in this case, I create a class or case class in Scala called borrower's ethnic background. This is my source data. This is my destination class. Here I'm going to turn it into a set of list data instead of create a nested column for this information. So I can see here that this is my data frame I'm going to create based on loan optimized. I'm going to use the as function to turn it into a data set. I'm going to map the various ethnic values, or excuse me, the race values to the actual name of the race. I'm going to put those together as a list. And finally, I'm going to create this class called borrower ethnic background as list. Excuse me. So I can see here that this is now a little more readable. So within Spark as well as in Databricks, you can set up nested columns. So rather than having those 4 different columns, which are kind of hard to read, I now have everything as a list of the actual ethnicities that the person had checked on their application. Awesome. Okay, so now that I have a couple of different modifications to this, I'm going to go ahead and save that transformation as a table, save as table loans transformed, and do a quick query to make sure that my data looks good. So again, it's running a distributed compute. It's actually executing that in the context. So one thing to note about this, and I mentioned this in my talk, generally it's faster to use user-defined functions in Scala because native is Java versus using Python. In this case, the engine has to go out to run this Python code and come back to the JVM to actually execute it. So it's not quite as fast as running things in native Java or Scala. Okay, so it's running in this case 16 different nodes. I can again look and see how it's progressing through the process. This is a much better view of kind of the overall explain plan. This is a more complicated query because I'm doing a join here. So this is what it's saying. It's actually looking at the data. It's shuffling the data across multiple nodes. It's joining those together using what we call the zip partition function. And this is where it's doing that evaluation of that Python function. And then it's actually doing whole stage codegen and mapping out the results and saving it to a table. So it gives you kind of a view of how you can actually do a little bit of introspection into how the underlying Spark engine is actually executing this particular workload. All right, finishing it up, a couple more tasks. And there you go. Now here's my new transform data set. One thing built into our notebooks, which is a nice feature, is the ability to actually look at data frames and seeing the actual columns. You can see that here. This is the new column called borrower race, which is an array type, as well as this new column called purpose of loan. I can also see that here in the display function. Here's my purpose of loan. If I scroll to the far right, I can also see here's my borrower's race. So likewise, you can translate these other columns that are part of this data set as you kind of go through your data munging. Talk a little bit about how you can do some enrichment of your data. So in this case, I'm going to join my data set with actual names of states. So you can see here, if I go back up to this transform data set, that the state code is a number. It's actually not very useful. It's a USPS code 55. I don't know what that is. So I downloaded from the internet and loaded into in this case, a MySQL database, a table called FM states, which is a list of the various states. Here they are. They're the various states codes listed here, and then here's the county that it belongs to. I can get the unique list of the states here, write it out to a file, and then I can join that same table based on the USPS code and create a temporary view called SFH that has that information. So a quick query to see if that worked. So it's going to run in the background, fix it off. So yeah, here's my states. I've done an average of the unpaid balance by state. I can also use a built-in visualization again within Databricks to see how that looks from a map perspective. So I can see here that the West Coast, since I have the most amount of unpaid balance, makes sense. Houses are fairly expensive. And then you can also see spikes here in the Northeast as well as in Colorado. I could also do some couple different visualizations using, in this case, looking at by different years. In this case, is looking at the aggregate across all the different years. But instead, I wanted to look at it. Let me run that here. Oh, I guess there's no data in 2010. That's probably why. Okay, there we go, 2012. So you can see here that you have different balances based on different years. Okay. So I have another table here. So if you've actually done some big data in, let's say, Azure HDI, Hadoop Insights, you'd be used to something called Hive, which is another SQL engine built into Hadoop. So one of the integrations between Spark and Databricks and HDI is the ability to actually import Hive data sources. In this case, we're looking at a table called zip code metro map. It's actually a Hive table. I can actually see that here. I can see here that this is actually a Hive format here, the Hive survey. And so you can actually connect your Databricks environment to your Hive sources, so you can actually read in data from Hive. So again, this is the data set I'm looking at here. I'm looking at the list of metro areas in the US. So Montgomery, Alabama is one. Here's another one in, let me scroll down a little more to one that's more recognizable. Alexander City in Alabama. So it gives you kind of a metro view of the various pieces of data. But I want to join this to my original source to actually look at the loans not by a state basis, but instead look at it based on a certain metro area. So rather than looking at all of California or all of Washington, I want to see like what are the metro areas that have the highest unpaid balances. So when I click create to do that, here I'm going to actually sum the unpaid balances by the CBSA name or the metro area, and then order it by that same column using the order by to command, and then sort it descending as well as limit it to the top 10 rows. So we ran this query before. It take about a minute. Yeah, so again, these are the metro areas. That's a little bit more recognizable. So you see Philadelphia, Camden, Wilmington are all considered one metro area, as well as, oh, I think that's most of this in this subsample data set. See that runs. Give it one more minute here. Yep, two more. And there we go. Double check from, yep, there we go. Okay, so this is the top 10 metro areas in terms of the loan balance. A little hard to read this as a pie chart. I might just turn it into a simple, let's just do a table view first. So the most outstanding loan balances are actually in New York, New Jersey, as well as Long Island. Second most is Los Angeles, and the third most is the Washington, Arlington, Alexandria, Tyson, Corners, DC area. So it gives you a quick way to do some quick analysis. So we're running a little short on time. I'm going to skip over this machine learning on this particular data set. I'm going to jump over to a little bit, one last example around how to use structured streaming. So in this case, I'm going to use a different data set. Because this data that I was using before was static, there wasn't anything to actually show in terms of streaming sense. So in this case, I'm going to do some structured streaming on the Wikipedia edits data set. So Wikipedia famously posts in real time all the edits going on Wikipedia right now in real time. So I'm going to do some quick analysis and show you how you can take advantage of streaming for creating what we call continuous applications. So I'm going to import a few files. Here, I skipped over this. I apologize. So this is actually looking at things from a WebSocket. And so in this case, I'm looking at this. In this case, this is a IP address that belongs to the Wikimedia Foundation. And here's all the different activity going on in terms of the website. I'm doing a simple netcat of that to actually look at that. So I can then translate that into something that can be done in terms of our Databricks notebooks and structured streaming. So here I'm going to read in that socket. I'm going to give it that host name, and port. I can turn that into a data frame, which I call edits. So in the case of the edits file itself, let me do a little introspection of that. It's really a 4-column data set. I didn't give it any column names, so it's just going to use C0, C3. And then I can do a quick display of what those edits look like. In this case, it's a simple JSON format, so I'm going to use JSON tuple to translate it into a data frame. So I can see here actually edits as they come in from various, in this case, different countries. So you can see here ES is for Spain, F is for FR is for France, DE is for Germany. I can see the actual timestamps when those edits occur. But within notebooks, I can also look and see how many records are coming in per second. So not too many, 6 records per second. Oh, sorry, 37 records per second. And here's how they're coming into the environment. So these are actual real edits going on in Wikipedia right now as we speak. So that's kind of interesting. You can just kind of do a quick view to make sure that the connection actually works. Maybe you want to do something a little more complicated. Look at like the counts of the edits by, in this case, different channels, as well as like a certain window of time, in this case, 10 seconds, and do a group by that time window. So I do a display of this edit counts data frame, which is based on a SQL statement here. I can actually look and see, based on the different channels, which are really based on different languages, what is the what are the edits based on different channels? So it's going to start populating this graph, this dashboard in real time. So I can see here, J, I believe, is Japan. IT is Italy. ES is, again, Spain. And so as time occurs, you'll see that this graph is going to be updated in real time. So I go back to my query. We're grouping this in a window of every 10 seconds. We're going to update the graph. We're going to order it by that timestamp. And again, we're going to be grouping things by the count of the edits. So you can see that right here. So a lot going on in this example, right? And so in this case, you were doing all of this in real time, and you're actually just writing the exact same code you would in batch. So this is plain old SQL. So for all intents and purposes, you don't really worry about thinking about the fine-grained requirements for doing streaming analysis. Instead, all you do is write simple SQL, which gives you a powerful interface for doing real-time analysis. Go down here. So this is a couple other examples. So that was an example that may or may not be applicable for you guys. But one of the things that's important, let me see here, from the list of these. Going down here. Yeah, so this gives you an example of it by language. So I'll pause there for a minute. You can run this. You can also see that all running here in our notebook. So again, it's actually using a lot more tasks. I recall from before, it was using 16. But again, because streaming is a fairly heavy workload, it's adding additional nodes to my cluster to actually handle the additional load from all those edits coming in from Wikipedia. Okay, so you can kind of get a quick view based on a summary level of the various languages. All right, so we're running short on time. It was great having everyone here. A couple different books for you guys in terms of learning more about Spark. Spark: The Definitive Guide is just recently been released by O'Reilly. High Performance Spark by Holden Karu, as well as Advanced Analytics with Spark with Sandy Riza, Matei, as well as Josh Willis and Yuri. So a couple different things for you guys going forward. And again, just to emphasize, if you guys are interested in trying out Azure Databricks, the URL again is databricks.com/Azure or azure.com/Databricks. And thank you guys again. If you have any questions for me, I'll be available for a few more minutes.